This DVD has been produced by the New Zealand Ministry of Health. It provides information on the monitoring, sampling, field analysis and telemetry useful in small drinking water supplies. It is important to know what is happening in your water supply. Monitoring allows the person responsible for supplying the water to know if, for example, the turbidity is too high, or if the UV is not working, or if there is E. coli in the water. Microbiological sampling involves taking an amount of water and trying to cultivate bacteria to see if they are in the water. Field analysis involves small instruments to check FAC, pH or turbidity. Remote monitoring uses some kind of monitoring system to tell you what is happening in your water supply. How do we know that the three principles are working? We need to have quality control assurance, which means that your treatment and reticulation system needs to be monitored.
When taking samples from a treatment plant or reticulation system, health and safety can be a concern and needs to be considered. Safe access to sampling sites is really important. This includes entry into a confined space such as a reservoir or a pump or valve chamber. The hazards with doing this can include things like lack of oxygen, falling from ladders or even drowning. Now, sampling source water from a surface supply such as a river, well, that might mean you've got to wade into the river, and so you've got to be careful about that. Don't get washed away. If samples are to be taken from a lake, you may have to use a boat, and in that case, well, you've got to make sure that you're capable of handling the boat safely. Well, a second person should always be there just to help out if things go bad.
There are ways of doing things and tools available which can reduce the risk of an accident. Proper training and equipment for entering confined spaces or working around water might make the difference between getting a job done and having a bad day. The use of things like sampling poles that have clamps to hold bottles on the end are helpful. They can remove the need to enter water that is being sampled. The most important thing is to think about the workplace risks and hazards of the things you're doing. Then work out how you can reduce the risks.
When taking samples, a number of things need to be considered. Firstly, you need to make sure that the sample being collected is representative of the water you want to test. The whole point of sampling is to test a small amount of water, the results of which can tell you about the water as a whole. For example, it is not a good idea to take a microbiological sample from the surface film on the water, where the air and water meet, because things in the water here could contaminate the sample. You need to take the water from underneath the surface.
If you want to sample the water going into a treatment plant, you need to take it from the intake pipes or as near to the plant as possible. If you're using water from a lake, sampling the water from the other side of the lake wouldn't be representative of the water going into the plant.
If you are going to sample water from within the treatment plant, you need to think about what you are trying to find out. What it is you want the sample to show you.
Yeah. And if you're using UV disinfection, the inactivation of pathogens is instantaneous. If treatment involves filtration, the removal of pathogens also happens at the time of filtration.
That's right. So if you want to know if the process is effective, you can take the sample straight after the treatment process.
However, some disinfectants need time for the process to work effectively.
If you use chlorine as a disinfectant, then a certain amount of contact time is needed in order for the chlorine to inactivate the pathogens.
So if a sample is taken close to where the chlorine is added, the test results may show an inaccurate result. The sample needs to be taken further through the system.
Probably from the water in the contact or treated storage tanks.
In a reticulation system, the water at the end of the reticulation system is likely to be of a poorer quality than the water leaving the treatment plant. So you might want to collect a sample from the very end of the reticulation system, maybe at a household tap. If you're doing microbiological sampling, it's best to sample at the extremities of the system. If you want to know if the water in your system is retaining its FAC, you could sample twice, once at the treatment plant and once in the reticulation system.
Another very important problem is the potential for the person collecting the sample to contaminate it. If the person taking the sample is collecting it while standing in the water, they may contaminate the water. Bottles clamped to the end of a pole can be used to take samples in such a way that the sampler doesn't need to go into the water for microbiological sampling. The sample bottle needs to be sterile. For chemical sampling, the bottle needs to be chemically clean. For some analyses, preservatives may need to be added or reagents need to be in the bottle before the sample is collected. Laboratories will provide you with the correct sample bottles.
The lid must not be put on the ground when the sample is taken, as contaminants may get on the lid. In fact, the lid should be held the right way up while the sample is being taken. The bottle must be pushed through the surface of the water face down and then held towards the flow of the stream. In this way, contaminants from the collector's hands don't contaminate the sample. If the water is not flowing, such as in a lake, the bottle must be moved forwards to create a flow. See? If you're sampling from a boat, the sample must be taken upstream of the boat.
And once the sample's been collected, make sure the container isn't contaminated by putting fingers or pH probes or anything else like that into the bottle.
The sample must then be labelled with the details of the sample, the date and time of sampling, and the name of the sampler. It is very important to discuss the samples you are collecting with the laboratory that will be doing the analysis. They should be able to provide you with written instructions on how to take each of the samples you are collecting.
Now, it's not possible to test for all the pathogens that could contaminate a water supply, so what we use is one microorganism, the bacteria E. coli, to indicate if the water has fecal contamination. If any E. coli is present, then this should be seen as an indication that the source water is contaminated and your treatment processes aren't coping, or there's a problem of some kind. This should raise some questions. Has something changed in the catchment? Has someone moved cattle or sheep into an area upstream of the intake? Has there been a landslip in the catchment that's making the water dirty? Is the disinfection system ineffective due to the turbidity? Is there a problem in the reticulation system? I don't know, backflow for example. Should the chlorine dose be increased? Or should the whole system be shut down for a while so the problem can be found and fixed? You might even need to tell people to boil their drinking water until things are sorted out.
E. coli analysis needs to be done by a laboratory with the special equipment needed to incubate samples and grow the bacteria. Normally, a water supplier will collect a sample in a sterile container provided by the lab and then take the sample to the lab to be cultured. There are a number of ways to analyse for E. coli, but they all involve growing the bacteria and counting or calculating how many there are. And the number of E. coli in a sample tells you how badly contaminated the water is.
Worldwide, E. coli sampling is the standard way of showing their water is safe to drink. But microbiological sampling is not the only sampling that can be done. Things like free available chlorine, pH and turbidity can tell a water supply operator a lot about their system and how well it's operating. Larger water suppliers generally monitor their system's performance by using continuous online probes testing all the time. However, smaller suppliers will generally sample manually.
Chlorine, when it's added to a water supply, reacts with organic material in the water. That's how it inactivates bacteria and viruses. But this uses up some of the chlorine, and the chlorine that is left is called free available chlorine, or FAC. FAC reduces over time. Sunlight and warm temperatures also reduce FAC. So if you're using chlorine as a disinfectant, it's important to test the FAC to make sure you've got enough to do the job. But you need to test for FAC on-site, because if you take the sample and then wait a couple of hours to do the analysis, the results will probably change. You can test FAC by using an electronic analyzer with a digital readout, or using equipment that measures the FAC by the amount of colour produced when a reagent is added to the water. This is very similar to the method used for testing the chlorine in a swimming pool or spa pool, but much more accurate. They are pretty easy tests to do.
It's important to store any reagents used to do test kits according to the instructions. They need to be kept in a dark, cool place. The reagents will have a use-by date, and it's important to check this because out-of-date reagents can give an inaccurate result. So you need to throw all old reagents away. Test kits also need to be checked from time to make sure they're accurate. This is called calibration.
When you get an FAC test result, you need to understand and interpret it. Most likely, it will confirm to you that everything is okay. But if it is high, you might need to reduce the amount of chlorine you're adding. Or if it is low, you may need to increase the amount. Testing for FAC gives you the information you need to adjust the dose. But remember, the FAC test is for the chlorine that is available as a disinfectant after some has been combined with organic matter, not the actual dosage amount of chlorine. The FAC should ideally be greater than 0.2 milligrams per litre of water to make sure you have enough disinfectant to control bacteria and viruses. 3 milligrams per litre of water is too high and the water would taste pretty bad.
pH is a measurement of the acidity of water. It's measured on a scale from 1 to 14. 7 is neutral, lower than 7 is acidic, and greater than 7 is alkaline. Ideally, water suppliers should try to keep drinking water at a pH level of between 7 and 8. The level of pH is important in chlorinated supplies because a high pH reduces the effectiveness of chlorine. But if the pH is too low, the water can leach metals from plumbing fittings, which can be a health risk over time. So, keeping the pH constant at about 7 is important for water suppliers.
Well, in New Zealand, groundwaters often have a low pH of about 6 or 6.5. This is because the groundwater can have a high CO2 content. The pH can be increased by aerating the water, blowing bubbles through it, or trickling it over a rough surface. Aeration removes CO2 from the water, increasing the pH. Another way to increase the pH is to add lime or soda ash to the water. Sometimes the pH can be too high. This can be caused by the water flowing through or over limestone. The water picks up the calcium from the limestone and this increases the alkalinity.
In some source waters, the pH is very constant and it doesn't change much at all over time. Groundwater that comes from a bore which is not affected by surface runoff generally has a constant pH. But if the water comes from a shallow bore, the pH of the water may change every time it rains, and surface waters have pH that changes sometimes quite rapidly. Mostly New Zealand source waters have a low pH.
You can test pH with a similar kit to the chlorine test kits. A reagent is added to the water and the change of colour is compared with a colour chart. You can also get an electronic analyzer with a probe that you put in the water and it gives a digital readout. Just like FAC testing, the sample needs to be tested in the field just after being taken because sunlight and time affect the result.
If pH tests show that the water doesn't change, you can reduce the pH test to as low as 1 a year. But if the pH of the water changes, you need to test it to get an idea of what the range of variation is and what causes the changes. If you're using chlorine, you need to monitor the pH to ensure the chlorine continues to be effective.
The temperature of water can be important in treatment processes and sampling. Microbiological samples need to be analysed as soon after they have been collected as possible, within 6 hours. While they're being transported to a lab, you need to make sure they don't get too warm, or any bacteria in the sample may multiply. The best thing is to try and keep the sample at the same temperature as it was when it was collected, or a little cooler. It's good to carry the samples in a chili bin with a cool pad in it. This should keep the temperature between about 4 and 10 degrees.
In some water treatment processes, the temperature can be important. So if the water is too cold, the process happens very slowly. What it may mean, is that in winter, when the water is colder, the flow rate through the filter will need to be slower. And chemical reactions, they are affected by temperature as well. They go faster when the water is warmer.
In water treatment plants using UV or chlorine to disinfect the water, dosages may need to be adjusted according to the temperature of the water. In warmer water, the disinfection becomes more effective, and in colder water, it's less effective. And with chlorine, the temperature could also affect the contact time that's required. So the most important thing about water temperature is to know what it is at different times of the year so you can understand how it might affect your treatment processes.
When you're testing the temperature of source water or water in a water treatment plant, it's best not to put the thermometer into the actual water. If you're using a thermometer and it breaks, it'll release mercury into the water. But also, if you're using a temperature probe, you want the water to be still, not flowing. The best thing to do is to take a small amount of water into a container and test this.
A turbidity test tells you how dirty the water is. That is, how much suspended material is in the water. It's measured in units called nephelometric turbidity units, or NTUs. This analysis can be done with a portable turbidimeter. To test turbidity, you take a sample of the water and put it into the turbidity meter. The instrument measures turbidity by shining a beam of light through the water and measuring the intensity of light that passes through.
These instruments are pretty sensitive and measure differences in turbidity that you couldn't see with the naked eye. For example, by looking at a number of different samples, you wouldn't be able to tell the difference between 10, 1 or 0.1 NTU. But 0.1 NTU would be very good turbidity for drinking water. 1 NTU would be only just good enough, and 10 NTU would be considered unacceptable. A normal clean-looking river would be about 10 NTU, but a dirty river in flood could be up to 5,000 NTU.
It's difficult to test water for a protozoa, so turbidity is often used as a substitute for protozoa testing. The idea is that if the water has low turbidity, say less than 0.5 NTU, there is very little risk that it will contain protozoa cysts. The more turbidity, the more chance of protozoa.
Measuring turbidity is a good way of knowing how well your treatment system is working, because it tells you how clean the treated water is. Some water supplies actually automatically turn off and alert an operator if the turbidity of the treated water gets over a certain amount.
The instruments used to measure the water quality, like any other equipment in a water supply, need to be maintained on a regular basis, otherwise they could give incorrect information about the quality of the water. The instruments need to be calibrated from time to time. Calibration is the process of comparing the results the instrument is giving to a known value, a reference standard, or a laboratory test.
For example, to check if a FAC test kit is still accurate, we could ask someone from a laboratory to come out to the treatment plant and test a sample at the same time we take a sample. We could then compare results. If our instrument is not reading the same as the lab sample, we could then make a change to the instrument. Another option could be to send the instrument away to a lab or the instrument supplier for calibration.
How often you need to calibrate each instrument will be outlined in the instrument manufacturer's instructions. However, if your instrument has been identified in your PHRMP as being critical, then you may wish to do the calibration more often.
Telemetry means to measure from a distance. So telemetry is an electronic system which monitors the apparatus at the water treatment plant and lets the supplier know what is going on at their plant without them having to travel to the plant. Telemetry usually uses something like a wireless system or the cellular network to let the supplier know if their turbidity is too high or if their FAC is too low, or other information like that.
A slightly more advanced usage of it is to give you early warning of something that's going wrong. For instance, if you're going to have run out of water, it would be nice to know about it before some irate person calls you up and says, I've turned the tap on and nothing's on.
You can get information about just about anything using telemetry. It's just a case of connecting the instruments, like a turbidity meter, up to the system.
Yeah, but you need to think about how much information you need. Like, do you want to know if the turbidity is over a certain level or exactly how high it is?
And do you need to know just that the UV system is not working, or do you need to know the level of transmittance?
What about for small drinking water supplies?
Well, probably the most helpful use of telemetry is to just have a simple alarm to let you know that something's gone wrong.
That's right. And if you set up the treatment plant so that it shuts down if the chlorine runs out, or the turbidity gets too high, then a pager can let you know that there's a problem.
Yeah, and then you just run down to the treatment plant and see what's going on.
And if you've got enough storage, you can keep supplying water while you get things fixed.
The water supplier needs to have a system for their particular situation and a system to give them the type of information that they need. For small supplies, a simple alarm to let the person responsible know if something has gone wrong can be very helpful, and make sure that they don't provide water that's not safe to drink.
If you are responsible for the supply of safe water, it's essential that you know what is happening in your water catchment area, in your treatment plant, and in your reticulation system. If, for example, heavy rain adversely affects the turbidity of your water, your UV system may not be able to operate to its capacity, and pathogens may be getting through the treatment plant and into your reticulation system. In other words, the small provider, no less than a large water treatment plant, needs to have quality control. And for quality control, the water supplier needs to know what is happening at each stage of water collection, water treatment, and water distribution. This means that the water supply needs to be monitored at all stages, from source to treatment to tap supply.